I have two different titles up here. The first one is the one I'm going to talk about today, looking at self-assembled monolayers of alkane diols on gold surfaces. This project is one that I worked on last summer as a SURE project. It's something I'm interested in continuing, but it requires travel to Tufts University every day, or most days of the week. So it's something that would strictly be a SURE project and not so much for research. But if anybody's interested in gas surface reactions, let me know and we can talk. We have some more projects that I'm going to be working on here. But since I only have 45 minutes, since we only have a few minutes, I'm just going to talk about the first project. And currently, right now, I have 3 students working on it: Alexa Stathis, Kat Hansen, who's here, and John Hedges, and then Sean Dwyer worked on this project with me. So this is kind of in conjunction with another group at Tufts on the Early Psych Lab, where we do STM work. I just grabbed a picture off of his website, and then he did really cool stuff like red snake and apps. And so we can't do that, but we get to take them out there and visit their hands and stuff like that. So first of all, why do we care about self-assembled monolayers? So it turns out that sulfur and gold really like each other. So if you take hydrocarbon chains, put a sulfur on the end, and just put it in solution near a gold surface, it's going to stick to the surface. And if you get enough of these together on the surface, they all stick and they all line up and they form what's called these self-assembled monolayers. So automatically on their own form a nice patterned structure on the surface. And one of the reasons this is studied often is ease of construction. It's really easy to make these. Like I said, you just need to get these in solution and they'll stick to the surface. I have ease in quotes because that's what every paper tells you. It's really easy. It turns out that it's not always that straightforward, as we found out in the past few months. But you get a really good idea. You can really study carbon chain interaction as these things are lined up. How are the carbon chains interacting with each other? Why are they staying together? Why are they patterning themselves in a given way? And you can also look at the interaction of the sulfur and the gold using Raman spectroscopy, which is something we're going to be doing. If you functionalize these, if you put different functional groups onto the hydrocarbon chain, they can be used for nanopatterning, for molecular electronics. Also, if you think about it, now you have, if you take a gold surface, an exposed metal surface, and now you cover it with a hydrocarbon surface, it's kind of a wetting inhibition type of study, so you can make things hydrophobic that maybe once before were hydrophilic. Also for biosensors, feature different biomolecules, and actually study how things react. And so these are kind of the reasons that get you interested in a project, and this is the reason that you keep doing it. Because there's applications for all these things, but once you start working on it, you realize you really want to know just what's going on. Why are these things lining up so well? Why are the interactions so strong? And what certain functional groups will do becomes really interesting. What am I doing for time?
You're at like 3 minutes.
Okay. So, quarter done. So, what is SEM? So, scanning tunneling microscopy. If you think about, you bring 2 wires together. Classically, if you put a voltage across them, you would get no current across. But it turns out that if you get things really close together, you can get what's called tunneling. It's almost analogous to a static electricity spark. So you get jumping of electrons from one wire to another. In this case, we have a tungsten wire, which is really close to a conductive metal surface. If you put a small potential across that, you can get electrons to jump from the surface to the tip. And the current that you get coming from the surface to the tip depends on how far apart the 2 surfaces, the metal tip and the metal surface are. And so what you can do, there's these really cool things called piezoelectronics or piezostacks, which are really thin films of metal that if you change the voltage across them, they change size in really small increments. And so you can move things on the picometer scale. And so what you do is basically in STM, you bring this conductive tungsten tip really close to the surface. You measure a current, and what you do is you scan across the surface, and you try to keep that current the same. So if you get to a point where you come to a bump in the surface, your current will increase because you're closer, so your tip's going to move away. And what you can do is map how much your tip is moving and get basically a topography view of the electrons on the surface, which is really cool because you see essentially single individual atoms on a surface. And so atomic resolutions of surfaces, and basically you're probing the electronic structures of the surface. And we can use this in our study. We can look at gold surfaces, and then basically we put things on it and see how things assemble on the surface. So this is The setup, I showed you the picture in the beginning, which is really kind of a complicated instrument. That one actually gets down to 4 Kelvin. This one is basically room temperature. And so this is the whole STM here. There's a controller and the STM head here, and it's hard to see, but there's a platinum iridium wire right here, and there's a graphite surface or a gold surface right there. And they come in really close contact, so my woman warning. They come in really close. I don't have to do the questions. You bring them really close together, you set it to be a certain current, it scans across the surface and gives you a topography of the surface. So this is images of, this is graphite, clean graphite, and this is gold. Graphite here, if you look at the size of this, it's 2.5 nanometers. So it's on the order of the size of atoms, so you're looking at individual carbon atoms on a graphite surface. Is that my time? And then this is a gold surface. Gold is a much flatter surface, so we can't get atomic resolution on gold, but we can see step edges on the gold. And this is just a map. If you took a cross section of this, and the top on the surface. Here is that clean gold surface again, and then we're able to absorb a mixture of 2 different thiols on the surface, and actually look at the difference in heights of the 2 thiols on the surface. So we've been able to get the thiols to absorb. What we really want to do is get thioethers, and so basically it'd be just like the thiol, but you have the carbon chain on either side of the sulfur. Nobody's really gotten good pictures of these on the surface, and the whole idea is maybe these things laying flat instead of sticking up. Also, we want to start doing Raman spectroscopy to characterize the interaction between the carbon chains and also between the gold and the sulfur on the surface, and also increase the number of sulfurs in the chain, so you can have sulfurs, 2, 3, 4 sulfurs, and make long chains absorbed on the surface. Again, functionalize the hard hydrocarbon chains. You can get into molecular wires, and also kind of more collaboration with Charlie Sykes at Tufts University and get some time on low temperature STM, which would be really cool. Questions? See, you know these This is the world record world's smallest video. Basically, these are copper surface with iron atoms, and basically they made a video at IBM Research. Each frame they went and they moved individual atoms to make this video.
It's like clay animation with that.